Hi everyone, I'm Richard Lee. I'm a research scientist in Meta. Today I'm presenting LongTale towards automatic performance anomaly explanation in microservices. This work has been done when I'm a PhD student in University of Utah. Cloud computing today is migrating from monolithic to microservices to achieve better scalability, faster development, and faster deployment. However, this benefit comes with a cost. When there's any performance issue happen, it's very difficult to identify, explain, and resolve. Let's look at a very simple example. Here's the CDF of RPC latency. The RPC is serviced by 5 service instances. From this picture, we can ask many questions. First of all, is this long tail, a normal tail, or an abnormal one? Because we don't have a baseline to compare with, we don't even know whether it is abnormal or normal. Let's assume it is abnormal. We can also ask more questions. For example, which service contribute the tail the most? Is one service being the culprit, or all the services are to blame? Or if the anomalies are scattered around in the services? All these questions, we take this scenario as a motivating scenario that in the microservices, there's a kind of scattered microburst of resource saturation that can contribute to this kind of long tail latency, and it is very difficult to explain it. Services can be similarly abnormal, and coarse-grained performance monitoring tools cannot explain it, and they can be sparsely spread out so that you don't even know where to start. And application layer tracing is limited that some of the events are not happening on the execution part of the application layer tracing, and container orchestration or autoscaler are too coarse-grained to handle it. The goal of this paper is to explain this anomaly scenario automatically. As a motivating scenario, we are not limiting our paper to only handle this in case. The solution of our paper is what if we can compare the slow and the fast so that we know what is going on in the slow requests. This simple question is actually not very easy to answer. There are two main challenges. First of all, existing tracing tools are limited. There is no sufficient data for us to do the comparison. Second, there is no clear way to effectively compare the trace to extract knowledge for troubleshooting. Today, this paper is sharing the way we handle these two challenges. Before we go to detail, let's look at the deployment here first. So this is the microservice application. We have 3 virtual machines, and on each virtual machine, we have a bunch of containers on it, and each container there's a application layer tracing client to collect traces and then send it to application layer tracing agent and then send it to the database. Besides that, we have a system stack trace collector, and we collect the system stack traces at a pace of 1,000 times a second and then send the data to the analysis node. We go through a 4-step processing to get the explanation. First of all, stitching. We stitch the application layer tracing with system stack traces. Here, the picture shows as time goes by, there are fast requests and slow requests. We give the fast request as green bars and the slow request as red bars. And these are the application layer tracing. Each span has information of its name, its start time, and end time. Meanwhile, we also have system stack traces. One slice of system stack traces is essentially a snapshot of the system, which shows which process is on the CPU and give you a call chain, for example, function A calling function B calling function C, with the start time of and end time of the span and this sequence of system stack traces. We can do the slicing that, for example, this red bar of span, we can slice to get this sequence of system stack traces. And then we can see that in the slow span, abnormal span, there are more like anomaly process showing up. And in the short span, they have a bigger fraction of user processes, which is the processes doing the real work. Sometimes when the span is too short, sometimes the user process is not showing up because we are doing sampling. We are sampling 1,000 times a second, so it is some chance, they have some chance to miss it. But this also tells us that a singular span does not reflect the execution state of the system. We need to aggregate multiple spans to make a statistically stable view of the execution state. This is how we do the aggregation. We put together, we randomly select a bunch of fast spans and put them together to make up a 10 seconds duration. And then we randomly select slow spans to put together to make up a 10-second duration. And then we construct this frame graph as such. From this picture, you can see with the fast execution on the left, the stress ng takes less than 1% of the CPU time. And on the right, the 0-1, the stress ng takes more than 13% of the CPU time. From this picture, you clearly can see stress ng are probably the main contributor of the slowdown. But again, this is just one single data point. We want the aggregated view to show the statistically stable analysis. So we generate 10,000 vectors from this aggregation and make a table like the right table on the table on the right. The table, each row is a vector, each column is a feature. The feature is essentially a function's name and the fraction of the function on the CPU at the duration. And we label this vector with its span duration. And then we feed this table into the linear regression algorithm. Here we use ElasticNet for our linear regression. What ElasticNet provides is that given a table like such, it will analyze to show the coefficient of each feature related to the result. We can know how correlated each feature is related to the duration of the span. You can see here the green line, the green solid line is the normal case, that there is no anomaly injected, and it is very flat. In mathematical language, its standard deviation is very low. It is way lower than others. And we do many experiments, and then we pick the threshold of 10 as our threshold to tell it is a normal case or abnormal case. We have false positive and false negative analysis later on in the paper. We use the 99th percentile to decide whether a feature is an outlier feature, to decide it to show it is a culprit. And from this picture, stress ng is standing highlighted as a culprit. To evaluate this idea and paper, we asked a few questions. Can LongTale explain a normal tail latency? Is LongTale service agnostic? How is the completion time and other use cases? For time limitation, I will show some result here. We evaluate our system in the real world cloud system using six hardware machine and using OpenStack and Kubernetes and Sockshop and Locust as workload. In this experiment, we are trying to understand under different intensity of anomaly how things going. First of all, we have the baseline as normal. As you can see, the standard deviation is way lower than others. And the second column of this table is the description of the microburst, which is the intensity of the anomaly. And then we draw a plot like this. From this plot, we can see that the stress ng are clearly highlighted as the culprit of the slowdown. We also visualize when and where the anomaly happens. And we also have experiment to show that LongTale is working with different language, different application. We run this experiment 10 times to show the false positive and false negative rate. There's the outlier data point, which is payment, because after we look at the code, it is implemented as echo server that the span of the duration is very short, and this does not work very well with the LongTale. But the takeaway from this table is that LongTale was for different types of microservice derived in different language without any domain-specific knowledge. And we also do experiment with different performance interference factors. Experiment shows that LongTale can highlight all these performance interference factor clearly, and the coefficient that it discovered is in line with how we designed the experiments. To summarize, it is feasible to automatically explain performance anomaly in the cloud by stitching application layer and system level tracing in an application agnostic and immediately deployable fashion. Thank you.